Okay, so the next topic we're going to cover in a little bit of detail, is fluid statics. All right, and that's simply a situation where fluids are at rest. And the first aspect of that is that pressure, the pressure distribution of a fluid at rest within a gravity, under the influence of gravity, is it varies as a function of depth only. Okay, so first, what do we mean by pressure? So let's just kind of rehash some stuff. So pressure is a force divided by area. And in this particular case, we have the weight of the fluid bearing down on a given section of the fluid itself, or you could say the floor. So this floor has to support the weight of all the fluid above it. All right, this floor has an area. You know what I mean? And this, what I'm saying, is actually equally true for any cross-sectional surface, as well. And so the weight, in this case, the force is going to be the weight, which is the mass times gravity over the area, and then the mass is just the density times the volume times gravity times the gravitational constant divided by the area, and then the volume divided by this area that I'm talking about, which would be the area perpendicular to the z direction, would give you just the height. So that's just kind of a hand wavy way of deriving this, but essentially, as a consequence of the weight bearing down, with the weight of the fluid bearing down on top of it, the pressure builds as you go down in depth. All right, and we use H, unfortunately, as the same as the symbol for the depth. All right. Now, what is meant by absolute and gauge pressures? There's an atmospheric pressure that is acting, all along every surface in this thing. So this is again P naught, which is basically the atmospheric pressure. And so, as you can tell, if this line indicates, this line right here is an indication of the pressure, right? But it doesn't start at zero. It actually starts at P naught. So the absolute pressure starts at the atmospheric pressure at the surface of the fluid, right? The pressure just above the surface is atmospheric, but then the pressure, right at the surface is atmospheric, but then it increases as a function of depth. Now this is true for air as well. It's just that the density of air is much smaller than, say, water. It's by a factor of 1,000. You know what I mean? So pressure does vary as a function of depth, like the fact that we have basically 14.7 psi of atmospheric pressure. That's a consequence of the 200 and some odd miles of atmosphere you have above you. Whereas to get that same thing, you don't have to go down a few feet to double that atmosphere once you're in the water. All right. So oftentimes we're interested in the sort of the net force acting on a surface. So in this particular case, we have the atmospheric pressure. What we have is a container, the corner of a container. We have atmospheric pressure operating on the outside, and then atmospheric plus the pressure due to the variation in depth operating on the other side. And so the net would simply be the absolute pressure, as described here, minus the atmospheric pressure. And so what we get is what's called gauge pressure. And so PG is just the absolute pressure minus the atmospheric pressure. Okay, so in many instances, what we're interested in, or depending on your device, you may be measuring what's called the gauge pressure. Okay, so the pressure varies with the function of depth. So if I had, say, a container that looked like this, or maybe I had a container, any arbitrary shape, and it's filled, imagine the bottom of this container is level with this one. And they're filled to, say, this height. And then we had basically just a long skinny tube, and it's filled also to this height. So the pressure at this point on all of them is equal. So the pressure here is equal to the pressure there, is equal to the pressure there. All right. So we fill them all up to the same height. The pressure here and here and here are all the same. So not only does pressure vary with depth in a static situation, it's only dependent on depth in a static situation. Okay, it doesn't depend on, like, there's very little fluid above this one in this particular case, and much more, say, in this particular case, and maybe even a little bit more in this one. However, there's more area to distribute that force, so the pressure remains constant. So pressure is only a function of depth in a static situation. Now we can use this. This principle is used as a measuring. This principle is used, say, as a means to measure pressure in a device called a manometer. All right. So if I have a vessel, and out of that vessel I have a tube, this vessel operates at a pressure P, and then this, I have some sight windows or something like that, and I'm able to measure this height. So say I have air maybe inside of a chamber, and then inside of this tube I have water, say. Well, the air pressure is going to be pushing down on this end of the column, causing this end to elevate. And the pressure the gauge pressure within this column is equal to rho, the density here, times gravitational constant times h. Okay, so we have a device, and a lot of times you actually, like if you listen to the weather forecaster, they'll give pressures, barometric pressures, in terms of heights of fluids, inches of mercury, stuff like that. Okay, a lot of times fan curves, the pressure drop given in a fan curve will be given in inches of water. So we have a height of a fluid is actually a unit of pressure. Okay, so you'll see that a lot. And this is exactly how you translate from that height of a fluid to some other pressure unit. Then the second topic that we're going to be talking about in fluid statics is that of buoyancy, which is actually very similar. It's a very similar force. Okay, so the buoyancy force acts on the centroid of a body and it's an upward force when that body is submerged in a fluid. Okay, so say I have an arbitrarily shaped body. It's submerged in a fluid. There's a buoyancy force, F sub B, with it's upward. It operates on the centroid of the body, right? So the centroid being like the center of volume. Okay, so it doesn't matter if this thing if it's heavier on the bottom or lighter on the top. The force of buoyancy operates on the center of the geometric center of the object. Okay, then say there could be some center of gravity, which is the distribution. The center of gravity would be like the center of mass. That has to take into effect any sort of distribution of the mass within the object. Okay, so it may not be co-located at the point at which the buoyancy force is activated. You follow what I'm saying? So if you have if you have a container and it has a bunch of heavy liquid in it or something like that, the buoyancy force is going to operate at the centroid, the geometric center, and the weight will operate at the center of mass, and they're probably not going to be co-located. However, the way the buoyancy force works, if I have the object, if I instead removed that object, I would have a void. Okay, so pretend that this is the same object. So object removed. The result is that this region of water was displaced when I inserted the object. Okay, so, or I'm sorry, this region of the fluid in question. So we'll just say that this is going to be water. So I had a region where there was water, and instead I removed that mass of water and inserted the mass of the object. As a result, there's a net disturbance, a net sort of removal of mass. And so the buoyancy force is equal to that mass that was displaced. All right? So I'll just call it displaced. Times gravity. So the displaced mass times gravity. Another way of saying that is that the buoyancy force is the density of the fluid times the volume that was displaced times gravity. And this is, you can see the mass is just density times volume, right? So dropping the subscript, buoyancy force is just the density of the fluid times the volume times gravity. And it's just a simple matter of that fluid was displaced. There's other ways of deriving this, but the fluid was displaced when I put the object there. And so there's a net upward force, a net, buoyancy force due to the weight of the water that was displaced. Okay?